Last time we entered y equals negative 16x squared plus 120x plus 80, and we looked at the window settings. We thought about the window settings. I'm trying to, trying to enter the function. I'm using x's rather than t's because that's what the calculator wants, x's rather than t's. Entering the function, h of t equals negative 16 x squared plus 120x plus 80. The 80 just happens to represent the height from which this arrow will be fired. 120 represents the initial upward velocity, 120 feet per second. The negative 16 has to do with the acceleration due to Earth's gravity near the surface of the Earth. And that's where that negative 16 comes from, but we don't have to know any of that. All we have to be able to do is enter this expression into the calculator and kind of know what the inputs are, what the corresponding outputs are. So if we evaluate this, well, I guess one more thing. We also looked at the window settings. The window settings, I set the x-min to 0. That represents the passage of time. So we're going to click the stopwatch right at the moment the arrow is fired, and it's going to start with 0 seconds, and then 1 second, 2 seconds, 3 seconds, 4 seconds. How long will the arrow be in the air before it completes its journey and heads back and hits the ground, hopefully very, very safely? I'm thinking about 10 seconds. It might be a little bit more than that, maybe not quite that long, but that's what my x max represents, 10 seconds. And the x scale is 1, so there'll be a little tick mark along the x-axis at 1 second, 2 seconds, 3 seconds, 4 seconds, and so on. How high is the arrow going to go? Well, I'm guessing no higher than 500 feet. If I guess it actually goes higher than that, that can be changed. But I'm guessing no more than 500 feet. So I'm starting with a y-min of 0, ground level. And it'll start at a height of 80 feet. It'll go up, it'll come down, and we'll be able to visualize its path. The y scale of 100 feet, so we look at this on our graph. We look at the tick marks on the y-axis, 100 feet, 200 feet, 300 feet, 400 feet, 500 feet, and so on. So I'm going to press the graph button. There we go. So if we wanted to determine how high is the arrow at a particular point in time, we could use the second value or second calculate value function. So press the second button. And then the trace button to get to the calculate menu. And number 1 on the list, value. And we're inputting time here at 0 seconds. At the instant the arrow is shot, it's at a height of 80 feet, 80 feet above the ground. We're trying to determine how long it takes the arrow to reach its maximum height. This section had to do with finding relative maximum points, relative minimum points. So how long does it take to reach its maximum point? Second, calculate number 4 on the list for maximum. Looking at it, it looks like it's about 1, 2, 3, maybe almost 4 seconds that it takes. So for a left bound, just to be on the safe side, I'm going to say 2 seconds. A right bound, I think I'll be on the safe side if I input 6 seconds. I think it happens somewhere in between 2 seconds and 6 seconds. It reaches its maximum height, and it looks like it's about 4 seconds. So I'm just going to choose 4 as a guess and press enter. It searches, it comes up with 3.75. And although there's a little bit extra there, I think this is close enough to 3.75 to call it 3.75 seconds. The y coordinate represents the height of the arrow at any given time. So we can go ahead and use that to answer the next question. What is the maximum height attained by the arrow? So 3.75 seconds, and then the maximum height attained by the arrow is 305 feet. And was there a C part? How long does the arrow remain in flight? Well, what does it look like? How long does it take to hit the ground? About 8 seconds. If we're solving this graphically, we're looking for a 0 of this function. So I'm going to go second, calculate, number 2 on the list for 0. Actually, we're finding an x-intercept, and we'll know the x-coordinate of that point is that 0. So press 2 or enter. For left bound, looks like it's happening between 7 seconds and 9 seconds. So I'm going to go with 7 for the left bound, 9 for the right bound. So somewhere between 7 seconds and 9 seconds, it looks like it hits the ground. I think it's about 8, so I'm going to guess 8. And it's going to search, and it's going to come up with 8.1 seconds. The y-coordinate of that point, -3e, -11, is technically scientific notation, but I like to think of it as a fancy way the calculator has of saying 0. Okay, 0. Officially, that's -3 times 10 to the -11th power, or about -300 billionths. It's hard to say -300 billionths, but yeah, -300 billionths, and that's a fancy way basically of saying 0. Okay, so 8.1 seconds is what we want there. 8.1 seconds. Given that the function is given, and we don't have to come up with it on our own, like we did in the case of the rectangular pen, where we had to express the area, total area enclosed by the pen in terms of the width x, I think this is a somewhat less difficult problem. It's just a matter of taking the function, realizing what it's telling us, inputting that to the calculator, and then finding the values and interpreting the inputs and the outputs. Still in section 2.1, piecewise defined functions. From the student perspective, I've got to believe that piecewise defined functions must seem like just an effort by math instructors, maybe the math department or the establishment in general, to take something that's not all that difficult and just make it more difficult, maybe unnecessarily so. So just to throw out an example of what we might see as an application of a piecewise defined function, there's a good example I ran across some time ago of a natural gas distribution company that charged their customers using different formulas depending on the amount, the quantity of natural gas that they consumed in a given month. So I'm going to throw out some rough numbers, but this will kind of give you an idea of how it was done. Let's say a customer consumes so many cubic meters of natural gas in a given billing cycle, let's say in about a month. Maybe they consume fewer than 100 cubic meters, or maybe they consume between 100 and 200 cubic meters, or maybe they consume more than 200 cubic meters. Let's just keep it simple there. Or maybe they consume none at all. Okay, so if the customer uses no natural gas, but their line is active, it hasn't been disconnected, it's an active line. If they turned on the gas, it would come on and they would be able to use it. They get billed something, some positive amount. I remember I was when I was in the process of moving from one house to another. The last time I moved, our local gas company, I remember the bill. Can't remember exactly how much it is, but it seems like it was in the neighborhood of $30-something, even though the total amount of gas that I actually consumed was 0 because we had already moved to a new location. But it was $30-something nonetheless. So some positive amount the customers get billed. And then if they consume more than that, they get billed per cubic meter. So if you look at the graph of how they decide how much to bill the customers, it would look something like that. You use more gas, it costs more. You get billed more at the end of the month. Now, customers that use more than 100 cubic meters get billed the same amount for the first 100 cubic meters as anybody else, but once they go beyond that into that second 100, the amount they get billed for each additional cubic meter is less than for each of the cubic meters during the first month. So if you look at the graph, for cubic meters 100 through 200, it looks like that. It's more. They're using more natural gas, and so they get billed more, but it's not as steep. If they continue to be billed like they were for the first 100, it would have looked more like that, just an extension of that straight line. But it's a line segment with a different slope. Finally, the heavy-duty customers that use more than 200 cubic meters in a given month have to pay for the first 200 cubic meters just like all the other customers do. But beyond that, they get billed in such a way that each additional cubic meter that they use is less expensive than the cubic meters from 0 to 100 and the cubic meters from 100 to 200. Now what we have is pieces of 3 different straight lines. If we looked at these straight lines, this one right here, it would have a slope and it would have a y-intercept. So you could say the equation of that straight line is y equals m sub 1 x plus b sub 1. It has a particular slope, it has a particular y-intercept, so you could write an equation of that line. And then there's the straight line that looks like that, of which that line segment where we decide how much to bill customers between 100 and 200 cubic meters, that's another straight line. And if we're going to write an equation for that straight line, we could do it. That'd be y equals m sub 2x plus b sub 2. And then there's that third one that extends as far as it could possibly extend, depending on how much a customer used. That's yet another straight line that looks like that. If we were going to write the equation of that straight line, that would be y equals m sub 3 x plus b sub 3. Different slope, different y-intercept. Now what we'd like to do, or what this gas distribution company would like to do, is write a function where they could just input however much natural gas that the customer consumes. Maybe it's that much, or maybe it's that much, or maybe it's that much, and have the computer calculate exactly what their bill would be based on the consumption. They can't use just one expression. It wouldn't be, well, multiply by m sub 1 and then add b sub 1. Well, that's what you would do if it's the customer down here that used fewer than 100 cubic meters of natural gas. If the customer used between 100 and 200 cubic meters of natural gas, this one right here, you'd multiply by m sub 2 and then add b sub 2. Or if it's the customer that used more than 200, you would multiply that amount by m sub 3 and add b sub 3. So the function would look something like this. Let's see, what would be a good letter of the alphabet? We can name this function. We could call it F if you want to, or something more descriptive. I prefer another different letter of the alphabet, or should we just use F? What do you think?
R. Rate.
R for rate. Okay, we'll go with rate. R of X, where X is the number of cubic meters that they consume, would look like this. Well, it might be m sub 1 x plus b sub 1. That is, if 0 is less than or equal to x and x is less than 100, or it might be m sub 2x plus b sub 2 if 100 is less than or equal to x and x is less than 200, or it might be m sub 3x plus b sub 3 if 200 is less than or equal to x. And another way to write that, you might see it instead of saying 200 is less than or equal to x, that might be written x is greater than or equal to 200, which means the same thing. It's defined in three different pieces because there are three distinct pieces of the graph, and they're pieces of three different straight lines, and these straight lines are defined using three different algebraic expressions, three different slopes, three different y-intercepts. So basically a piecewise defined function is a function defined by different algebraic expressions over different intervals of its domain. To sketch one, basically we need to consider each piece and plot enough points within each piece of its graph so that we can figure out what each piece looks like. In some cases where the pieces don't match up just right, there might be a gap in the graph. In a case like this, I don't think they would want that to happen. Customers might ask, well, why is there such a big jump between using 99 cubic meters and using 101 cubic meters? So if they could do it without a big gap in the graph, I think that would be to the advantage of the company. Fewer complaints that way. Let's just try evaluating a piecewise function. No particular application in sight here. Let's see if we can do it. For this particular piecewise defined function, let's see if we can find f of -2, f of 0, f of 2, and f of 5. In each case, the first question we ask ourselves, if we want to find f of -2, where is -2? Is -2 less than or equal to 0, or is -2 greater than 0? -2 is less than or equal to 0. So we use top expression. F of -2 equals 4 minus -2, and that's 6. We only use the top expression. It's a piecewise function and defined in two pieces, and I put this problem on the test. Don't give me two different answers. Don't say it's 6, or maybe it's -5, which you could get, I guess, by using that second expression. It's just 6. The fact that -2 is less than or equal to 0 tells us only use the top expression. Let's go with 0 next. 0, is that less than or equal to 0, or is that greater than 0? 0 is certainly less than or equal to 0. So f of 0 equals 4 minus 0, which is 4. How about 2? Is 2 less than or equal to 0, or is 2 greater than 0? 2 is greater than 0. So to evaluate the function at 2, that's on the different piece, that's the x minus 3 piece, we substitute 2 for x in the expression x minus 3. And we get -1. F of 5. 5 is not less than or equal to 0. 5 is greater than 0. So f of 5 is 5 minus 3, which equals 2. In each case, we look at the number in the domain where we're trying to evaluate the function. Make sure it is in the domain. And if it is, determine which piece of the domain it's in. And based on which piece of the domain it's in, we know which algebraic expression to use to evaluate the function. Example 7. The directions were to evaluate this at those same 4 numbers, but to get an idea of what the graph of this might look like without looking at the spoiler alert graph right there down below, one would need to evaluate this at maybe as many as a dozen different numbers in its domain, really to see what's going on. So consider the function f of x equals x squared if x is less than or equal to 1, 3 if 1 is less than x and x is less than or equal to 4, and 7 minus x if x is greater than 4. Pick any number. It would be pretty easy to evaluate the function, but can we put those function values together and sketch a decent graph of this? Let's choose some numbers that are less than or equal to 1. Numbers that are less than or equal to 1. Let's go with maybe as far to the left as -2. See if we can evaluate this at -2, -1, 0, and 1. All of those are in this piece of the graph where x is less than or equal to 1. So for each one of these, we're going to evaluate the function by taking the number in parentheses and squaring it. So here goes. Square the -2. Get 4. Square the -1. Get 1. Square the 0. Get 0 and square the 1. We get 1. This is going to give us 4 points to plot. 4 points to plot. Basically, the x-coordinate is the one inside the parentheses, and the y-coordinate is the function value, so we can plot the points -2, 4, -1, 1, 0, 0, and 1, 1. And we'll plot those in a little bit. Next, let's choose some numbers between 1 and 4. Maybe we'll choose 4, but we don't want to choose 1 because 1 has to be less than x to be in this piece of the graph. So how about 2, 3, and 4? All right, let's go with 2, 3, and 4. F of 2, f of 3, f of 4. That's going to be, they're all 3's, aren't they? If x is between 1 and 4, including 4, but not including 1, f of x is equal to 3. This gives us 3 more points, 2, 3, 3, 3, and 4, 3. And then choose a few numbers that are greater than 4. 5, 6, 7. F of 5 would be 7 minus 5, and that's 2. F of 6 is 7 minus 6, and that's 1. And f of 7, we're using this rule to evaluate the function there. F of 7 is 7 minus 7, and that's 0. So 3 more points. 5, 2, 6, 1, 7, 0. So we have 4, 5, 6, 7, 8, 9, 10. 10 points on this graph that we can plot and see if we can figure out what the graph looks like. And maybe right over here is a good spot to do it. I'm going to go as far to the left as -2 and as far to the right as 1, 2, 3, 4, 5, 6, 7. As high as 4 and as low as, well, we may not have to go much below the x-axis. So plotting these points, -2, 4, -1, 1, 0, 0, and 1, 1, we have a piece of the graph of y equals x squared. We don't talk about quadratic functions for a while, somewhere in chapter 3, but this is a piece of the graph of y equals x squared. It's a piece of a parabola. It would continue upward to the right if we allowed it to do so. It looks like it's having a hard time understanding what I'm trying to graph there, or maybe I'm just really bad at connecting the dots with parabolas. That was a bit of a struggle there. So we have these points on the graph. Let's plot the points 2, 3, 3, 3, and 4, 3. Those are points on the graph. 2, 3, 3, 3, 4, 3. Connect those. It's still a bit of an open question as to what's going on between 1 and 2. There's kind of a big gap in the graph. We'll come back to that. Plot the points 5, 2, 6, 1, and 7, 0. 5, 2, 6, 1, and 7, 0. So it does like this. And it would appear that it continues beyond this. If we were to evaluate it at 8, we get -1. At 9, we get -2. What's going on between 1 and 2? If we evaluated the function at 1.5, what would we get?
We would be using the, where it's between 1 and 4.
1.5 is between 1 and 4. So we would use this rule, f of 1.5 equals 3. So we plot the point 1.53. What if we evaluated this function at 1.1? 1.1 is still between 1 and 4, so that would still be 3. Tamara.
Where did you get 1.5?
Well, oh, where did I get 1.5?
Yeah,
well, I'm trying to figure out. See, I'm looking, and there's this great big gap right here between 1 and 2, and I'm trying to figure out, does this piece connect up there? Just what's going on in between 1 and 2? So 1.5 is just, well, that's a number between 1 and 2. We're just using that to investigate what goes on in there. So 1.5, it looks like we would simply extend the graph over like that. So there's still a gap now between 1 and 1.5, so I'm pick another number between 1 and 1.5, maybe 1.1. So if we evaluate the function at 1.1, 1.1 is still between 1 and 4. So f of 1.1 would be what? It would be 3. It would be 3, so we would get something like that, and we would extend it still further. But what's f of 1? With f of 1, we use the x squared, and so that jumps all the way down to the 0.11. All the way down there to the 0.11. So basically, there's a jump. This is officially characterized as a jump discontinuity. There's a break in the graph, so it's not continuous. And because it jumps abruptly from as close to the point, see, if we extend this over, we can make this as close to the point 1, 3 as you could possibly want to be, that point right there. But it doesn't include the 0.13. Why does it not, can it not include the 0.13?
Because it's not included between 1 and 4. It's not included.
Yeah, if you evaluate the function at 1, you would say, where's 1? And you would conclude, well, 1 is less than or equal to 1. And so f of 1 is 1 squared. It can't include the 1,3 because if it did, if we shaded that in like that, it would fail the vertical line test. We have to decide between these 2 points that have an x coordinate of 1, which one is going to be a solid dot, which one's going to be an open circle. And so it's got to be this one right down here, the 0.11. So we put an open circle because the graph goes all the way over to and virtually touches the 0.13, just doesn't include the 0.13. We don't need an open circle over here though, because if we evaluate the function, this is actually a little tricky. If we evaluate the function at 4, 4.5. How would we find f of 4.5 if we had to? You know, 4.5 is greater than 4. So it'd be 7 minus 4.5. What is 7 minus 4.5? The 2.5, it seems like it should be more than that, but that's exactly right. 7 minus 4.5 is 2.5. So this graph continues up this way, like that. What if we evaluated at 4.1? What is 7 minus 4.1?
2.9.
It is 2.9, and that would put us really close to this point 43 right there. It's actually, that would be the point 4.1, 2.9. Well, it turns out that this graph is actually, we can make it as close to that 0.43 as we please by choosing x close enough to 4 so these pieces actually meet. And that's because if we put 4 in this expression or if we put 4 in this expression, we'll get the same answer. We get 3 either one of those expressions we use if we use the number 4. So those pieces, how does it look? Those pieces actually meet at that particular point. So there's no need for an open circle, just they meet at a common point there. So this would be the graph of this. It's a little bit painstaking to come up with the graph, but if we have enough points and we have an idea of what each of these pieces of the graph will look like, it can be done. Example 8, let's see if we can take the information from this problem and come up with a piecewise defined function. We can graph it if we want to. I don't know if we're going to want to, though. As a new employee of Company C, your salary is based on your sales volume in dollars, X dollars. If your sales volume for the month is less than $10,000, X is less than $10,000, your salary is $2,500. So as I don't have to read through the whole thing, but I feel like just stopping and scribbling something down here. If I want my salary expressed as a function of X, what I'm thinking is if 0 is less than or equal to X, and that's less than $10,000, my salary is $2,500, just like that. So if my sales are $5,000, that's less than $10,000. So the salary would be $2,500. If I don't sell much at all, they might not want to keep me around for the next month. But if they're confident in my sales ability and I just have an off month or something, then maybe they'll keep me around, even with low sales like that. If your sales volume is at least $10,000, how we would write that? At least $10,000, but less than $50,000, like that. Your salary is $2,000 plus 6% of sales. So $2,000 plus 0.06x. Will that make sense? So if your sales happen to be $20,000 in a given month, we take $20,000 and take 6% of that. 6% of $20,000 is $1,200, I think. And then add that to $2,000, and that would be $3,200. That would be your salary for the month, which is better than if your sales had been less than $10,000. If your sales volume is at least $50,000, if X is greater than or equal to $50,000, your salary is 12% of your sales volume. 12%. So 0.12x. We've expressed the salary as a piecewise defined function of sales X. What was your salary in the month of May? If your sales volume was $45,000, how would we calculate that? $45,000 is in the middle piece, right? It's between $10,000 and $50,000. So we have to use the middle rule. Don't get to take 12% of it, but it'll be $2,000 plus 6% of it. Like so. So $2,000 plus 2,700. So it would be 4,700. $4,700 salary for sales at the $45,000 level. If we were to graph this, we would see a function whose graph consisted of pieces of 3 different straight lines. This one would just be a horizontal line. It would be from 0 to 10,000. It would just be $2,500. And I believe the next piece kind of would pick up right about there and would be, well, non-horizontal. It'd have a slope of 0.06. And so it would be $2,000 plus 0.06x, so it would go up a little bit. And then after that, it gets actually steeper from that point, 0.12x. It would pick up from there, and then if your sales are way up beyond $50,000, then 12%. So that's lots of incentive to maximize your sales in a given month. There are a couple of my math lab problems. I don't think they're quite this involved. I think they're just 2 pieces rather than 3 pieces, but they will ask you to fill in the blanks, input an expression which will define a given piecewise defined function. There's some 3-piece ones. Well, the instructor created ones just have 2 pieces, but there's some my math lab created ones that have 3 pieces. But the good news there is you can click on Show Me an Example to help me solve this, and they should give you some ideas of how to do that. So write a piecewise defined function for the function whose graph is given below. Let's look at the piece on the far left. I get the impression that it extends infinitely far down and to the left in the direction that's indicated there. This one, when we get to that piece, we'll assume it extends infinitely far down and to the right. So I believe that this function has all real numbers in its domain. Notice a solid dot right there. So I believe the function is defined using the same rule from negative infinity all the way up to and including x equals 1. So our first rule, f of x equals some expression if x is less than or equal to 1. Can we look at this piece of a straight line and determine its slope.
Can we do it by using the points?
Just kind of pick a couple of points on there. If we picked, say, that point, and if we went up 4 and 2 to the right, what would the slope of that piece of a straight line be? 4 over 2, or simply 2. So it looks like the slope of that line, m sub 1 equals 2, and ordinarily I would suggest using the point slope point slope equation to do this, but we can tell by inspection the y-intercept of this piece of the graph. What is its y-intercept? Where does it cross the y-axis? 4. So b1 equals 4. The y-intercept is the point 0, 4. So for f of x, we could say it's 2x plus 4 if x is less than or equal to 1. If we wanted to evaluate it at 0, we would get 4, and it would give us that point. If we wanted to evaluate it at -1, we would get 2, and it would tell us to plot that point. So it's that piece of a straight line. Next piece of the graph is from this open circle to this solid dot. So it starts just on the other side of 1, does not include the 1, and it goes all the way over to 3. There's a solid dot at 3, there's an open circle at 1. So we have the or equal to bar at 3 and the strict inequality at 1. That's an easy one. It's a horizontal line segment there, so it's constantly equal to 5 all the way throughout there. So that's all we need. If we're going to evaluate this function anywhere between 1 and 3, including 3 but not including 1, it's going to equal 5. The other one may take a little bit more work, or may not. It picks up with x is greater than 3. We've got the open circle there. So x is greater than 3. Can you tell the slope of this piece of a straight line by looking at it? 1 down, 1 to the right. 1 down, 1 to the right. 1 down, 1 to the right. I'm thinking the slope, I'd call that, what? M sub 3 equals -1. Now the y-intercept, if we really wanted to figure that out, I think it's about 7. Now in general, you might need to use the point slope equation, so I'm going to use the point slope equation, and any point on this line will do. I'm going to use it with the 0.43, so here goes. Using y minus y sub 1 equals m times x minus x sub 1. Y minus 3 equals -1 times x minus 4. Y minus 3 equals -x plus 4. If we add 3 to both sides, sure enough, y equals -x plus 7. So the y-intercept is indeed 7, and we can write -x plus 7 for this, this final portion of the domain. How do you feel about this one? Is this doable? I think as long as we keep the pieces linear, this is not a lot of trouble. If we make it more complicated than that, if it's a quadratic piece, a piece of a parabola that we have to look at, we really need a more thorough study of quadratic functions, I think, to come up with that. But as long as each piece is a piece of a straight line, I don't see why we can't figure out the slope, use the points slope equation if we need to, and come up with this.